Okay, so now let's take a look at another way of representing equilibrium and understanding what the equilibria look like, which is looking at the best response correspondences and noticing that we can actually represent equilibria as the intersection of those best response correspondences. So in particular, let's revisit the example we just looked at and take a look at how that works. So in particular, in terms of equilibria in the war of attrition game that we looked at, with these particular payoffs, we had two pure strategy Nash equilibria, one mixed strategy Nash equilibrium, where the row player stayed with probability 1/3 and the column player stayed with probability 3/5. So in particular, let's take a look at what the payoff to the row player looks like as a function of their strategies. So if they leave, they get 0 for sure. And if they stay, what they get depends on what the probability that the column player is staying versus leaving. And in particular, we ended up with an equation that the payoff to staying is -2 times PC plus 3 times 1 minus PC. And then we can look at the payoff to stay, graph that. So here what we have on this axis is the probability that the column player stays. In particular, if that's 0, then the payoff to stay is going to be 3. So we start up here at 3, and then as the column player stays with higher and higher probability, the payoff to staying for the row player goes down because it's more and more of a chance that they're going to stay when the other player is staying. So we end up with this downward sloping line representing the payoff to stay, and the payoff to leave is always 0. And so in particular, what do we end up with? We end up with stay being the better strategy if PC is less than or equal to 3/5. We end up with leave being better if PC is bigger than 3/5. And we end up with exact indifference when PC was exactly equal to 3/5. So in terms of their better response or best response, in cases where we're less than 3/5, they'd rather stay. In case where we're greater than 3/5, we'd rather leave. And their indifference point is exactly when the column player is staying with probability 3/5. So in particular, we can represent that in terms of the best response. So we put 3/5 here. If we're looking as a mapping as a function of the probability that the column player stays, then the probability that the row player would like to stay is 1 as long as PC is less than 3/5. It's 0 when PC is bigger than 3/5, right? So they'd like to leave in this case, stay in the cases where we're less than 3/5, and they're exactly indifferent. They're willing to play anything, any mixture, in the case where the column player leaves with exactly probability 3/5. So this, what do we end up with? This is called the best response correspondence of the row player. Why is it a correspondence? It's not a function because it's not single valued. So right at this point of 3/5, we have lots of different strategies which are optimal for the row player. Basically, any mixture is optimal at that point. So this is called the best response correspondence. The nice thing about it is when we look at this graph, it's actually connected. So it's moving along nicely as we move as a function of PC. So the best response correspondence to the row player has this particular shape in this game. Okay, we can do the same analysis for the column player. If you go through and you look at the column player's payoff as a function of what the row player is doing and so forth, we can do the same analysis. Here we map out as a function of PR, what's the payoff to stay for the column player. If PR is 0, then this payoff becomes 1. So we start up here at 1. As PR increases, this thing is sloping downwards and eventually hits -2 if we set PR all the way equal to 1. The payoff to leave, again, is flat at 0. So what do we end up with? In terms of best responses for the column player, we end up with stay being better when probability of the row player staying is less than 1/3. So stay is better in here. Then leave is better, is the best response in the situations where PR is bigger than 1/3 and they're indifferent exactly at 1/3. So we can go through, we map out the best response of the column player. It's similar to what we just saw for the row player, except their indifference point is now 1/3 instead of 3/5, and that just represents the slight difference in the payoffs that we have in this matrix. We also have the best response of the row player as a function of what the column player is doing. So we have both best responses, and let's now put them together on one graph. So what we'll do is we'll keep track of the row player's probability of stay, so probability that row stays. And on the vertical axis, we'll keep track of the probability that the column player stays. So we want to put both of these best response correspondences on the same figure. And we already have the right axes, PR on the horizontal axis and PC on the vertical axis for the best response of the column player. But when we look at what we have for the row player, we have these two axes reversed from what we'd like to have on this figure where we put them both together. So what we're going to have to do is take the best response correspondence that we calculated for the row player and just flip it so the axes are reversed. Okay, so all we're going to do is take this figure and we'll just flip it over so that now we have the probability that the row player stays as a function of what the column player is doing, but we're having this on the horizontal axis and this on the vertical axis, so we've just flipped the row player's best response so that we have them both on the same figure. So now we can superimpose what the row player's best response looks like with the column player's best response. So we have what the row player is doing as a function of the column, what the column player is doing as a function of the row, both on the same figure. And equilibrium points are going to be where both players are best responding at the same time. So what does that mean? That means we have to be on both of these best response correspondences at the same time. So the equilibrium points are points of intersection of these best response correspondences. So here we have 3 different points of intersection, one up here, one here, and one here. So we end up having 3 equilibria in this game. And indeed, they correspond to the equilibrium where the row player row stays, column leaves. We have the reverse, so column stays. And then we have the mixed strategy equilibrium in the middle here, where they're randomizing with different probabilities, reflecting the fact that the payoffs in this game are slightly asymmetric. So putting the best response correspondences on this figure allows us to see the equilibria directly and find them just in terms of looking for intersection points of the best response correspondences. Now, obviously, this technique of drawing this out is a little bit special. In 2x2 games, it's quite easy to do. As we hit more dimensions, it's going to be a little more difficult to do this directly. But conceptually, it helps us understand what the structure of equilibria look like. Okay, so let's take a look at a slightly different structure. So actually, one thing you'll notice in this game is that the equilibria are sort of sloping downward in the sense that it's sort of an anti-coordination game. We should have one player staying and the other one leaving, or vice versa, and the mixture is somewhere in between that. We can also look at a coordination game and see what the structure looks like in that setting instead. So let's take a look at a very simple coordination game. So this is a game where we have 2 technologies, say an old technology, which gives each player a payoff of 1 if they both use it. A new technology, which is the superior technology, gives each player a payoff of 2. If they miscoordinate and they don't have the same technologies, they can't talk to each other, for instance, they each get a payoff of 0. So very simple technology adoption coordination game. We can take a look here at the payoffs to a given player. So here there's a symmetric structure to the game, so we just have to calculate the best response correspondence for one of the players, and that'll be enough. So we can keep track of what happens to, say, the payoff to the row player as a function of the probability that the column player plays old. So let's let PC be the probability that the column player is playing old. 1 minus PC then will be the probability that the column player plays new. So what's going to be the payoff to playing old? The payoff to playing old for the row player would just be 1 times PC plus 0 times 1 minus PC. So they're just getting PC. And the payoff to new, we've got 0 times this, 2 times 1 minus PC. Right? So we've got these two payoffs. We can graph those out. So the payoff to old is just PC. The payoff to new was 2 times 1 minus PC. So this goes down in PC, this goes up. Remember, PC is the probability that the column player is playing the old technology. So what does that tell us? Here, the new technology is better if the probability that the column player is playing using the old technology is less than 2/3. Old is better if the probability that they're using the old technology is bigger than 2/3, and they're exactly indifferent at a probability of 2/3. How do you get that? Well, you're just putting the two payoffs together. This is PC, this is 2 times 1 minus PC. Find the point where those two things are indifferent, and you'll get an answer here of 2/3. So that gives us a figure in terms of the payoffs, and now we translate that into the best response. So below 2/3, new is better. Exactly at 2/3, they could play any probability on old for the row player would be fine. And then above 2/3 on the other player playing old, then old is better, right? So if the other, say the column player is playing old, then this is the best response of the row player. Okay. So if we put those together, we can put that together on the same curve. Here we've got the best response correspondence we just had. For the other player, we just flip it over across the axes. We get the best response for the other. What do we find here? Again, for equilibrium points, both players have to be best responding at the same time. So we're looking for intersection points on the best response correspondences. One up here, one right here, and one down here. So here's a point where they're both playing the new technology. So the probability that they're playing old is both 0. Here they're with 1, and then the mixed strategy equilibrium is where they both play 2/3. Now here there's a coordination game, and here we see the equilibrium are basically in an upward moving situation as opposed to the downward moving situation we saw in the anti-coordination game, where they were trying to take different actions as opposed to this situation where the better responses involve taking the same actions. So we get a sort of complementarity here, which is reflected in players either both using high probabilities or both using low probabilities, or using some intermediate probability where they both end up being indifferent. Now, in terms of payoffs, obviously, what are we looking at? We're looking at a situation where they're either both using the new technology, so the probability of old is 0. Then we get the payoff of 2. If they're both using the old technology with probability 1, then we're getting a payoff of 1. And down here, where they're exactly indifferent, they're using the old technology with a probability of 2/3. Then we end up with the payoff of 2/3. So here we can actually talk about a ranking of payoffs. So the new one gives the highest payoffs to the players. The old gives an intermediate payoff, and the mixed strategy gives the worst payoff to the two players, where they actually only get a payoff of 2/3 because there's a substantial chance that they end up mismatching their technologies and end up not getting any payoff at all.